You are watching the technology that could rewrite the entire internet, but almost nobody truly understands how it works. This is the world of blockchain, a tamper-evident ledger that moves digital value with no central authority. Billions in cryptocurrency, supply chain secrets, even whole identities are secured by these hidden chains. But if a single link fails, the consequences are global. How does this system actually keep our data safe, and what secrets are locked inside each block? Every block on a blockchain is more than just a digital container. It is a carefully structured record built for security. At its core is a list of transactions, each stamped with the exact moment it was recorded. Alongside that is a reference to the block that came before, a cryptographic hash that acts like a link in an unbreakable chain. But the real secret lies in the block's own fingerprint, a unique hash generated by running all of the block's data through a mathematical function called SHA-256. That hash is always 64 characters long, no matter how much data is inside. Change even a single letter or number, a typo, a decimal point, anything at all, and the resulting hash is unrecognizable from the last. This is not random. It is a property known as the avalanche effect. For example, the word blockchain might produce a hash starting with 2C26B4, but change it to blockchains and the hash becomes something entirely different. There is no way to predict the output and no shortcut to reverse the process. This one-way fingerprinting is what makes tampering instantly obvious. If someone tries to alter a transaction, even by a single byte, the hash changes completely, and so does the link to the next block, breaking the chain. With each block header storing its own hash and the hash of the previous block, the entire structure becomes self-checking and tamper-evident at a glance. Integrity is not just a promise, it is baked into the very structure of every block. Inside each block, the list of transactions is not just a pile of records. It is organized as a Merkle tree, a branching structure that brings both order and efficiency. Imagine every transaction at the bottom as a leaf. Each pair gets combined and run through the hash function, producing a new set of hashes above them. This process repeats, layer by layer, until a single hash remains at the very top, the Merkle root. That root is a compact fingerprint for every transaction in the block, no matter if there are 10 or 10,000. If even one transaction changes, a single number or a single character, the entire Merkle root shifts. This means you do not need to check every transaction to prove one is included or to spot tampering. The root alone is enough. But the story does not end at the block. The Merkle root becomes part of the block's header, which is then locked in by the block's own hash. This hash, in turn, is referenced by the next block, creating a domino effect. Change anything in one transaction, and the Merkle root changes, which alters the block's hash, which breaks the link to the next block, and so on, rippling forward through the entire chain. The result is a cascading integrity. A single root secures thousands of transactions, and every block's security depends on the unbroken chain of hashes. This is what makes blockchain tamper evident on a massive scale. Every block is tied to the next, and every transaction is anchored by a root that cannot be faked without detection. A single transaction begins with a user, someone sending digital currency from their wallet. The process starts when the sender signs the transaction with a private key, creating a unique digital signature. This signature is not just a scribble, it proves ownership and authorizes the movement of funds. Once signed, the transaction is broadcast to the network, where it enters the mempool, a digital waiting room shared by thousands of computers and nodes around the world. Inside the mempool, transactions line up, often sorted by the fee attached. Higher fees rise to the top because miners and validators are more likely to include them in the next block. Each node in the network independently checks the transaction details, verifying the signature, confirming the sender has enough balance, and making sure the format is valid. Only after passing these checks does the transaction stay in the mempool, ready for inclusion. When a miner or validator assembles the next block, they select transactions from the mempool, usually starting with those paying the highest fees. The chosen transactions are bundled together, and the miner or validator proposes a new block containing them. Once the block is added to the chain, the transaction receives its first confirmation. But one confirmation is not always enough. As new blocks are stacked on top, each one adds another layer of certainty. The confirmation counter ticks upward, 2, 3, 6, until the network considers the transaction final and irreversible. Throughout this journey, every node continues to validate and relay information, ensuring that the entire process remains transparent and secure. The flow from wallet to mempool to confirmed block is a dynamic dance of data, trust, and verification, all happening in real time across a global network. Miners and validators are the gatekeepers of blockchain. Their motivation is simple: follow the rules and you get paid. In proof-of-work systems like Bitcoin, miners race to find a special number called a nonce. The first to solve the puzzle earns the right to add a block. With it comes a block reward and transaction fees. This competition costs real resources, electricity, hardware, and time. Cheating, like trying to fake a transaction, is almost never worth it. If a miner submits an invalid block, the network rejects it, and the cheater gets nothing. Honesty pays because the system is built to punish failure with wasted effort and lost rewards. Proof-of-stake blockchains use a different approach. Validators lock up their own coins as collateral. Instead of racing, they are chosen to propose or vote on new blocks based on how much they have staked. If a validator tries to rewrite history or approve a double spend, they risk losing their stake. The higher the stake, the more they stand to lose. The network's security depends on the assumption that most participants act honestly, because the cost of attack outweighs the benefit. But what if someone gains majority control? In both systems, holding over 50% of the power, whether it is computing power or stake, can tip the balance. This opens the door to a 51% attack, where a malicious actor can rewrite recent blocks or double spend funds. Ethereum Classic suffered this fate in 2020 when attackers reorganized thousands of blocks and stole thousands of coins. Even so, pulling off such an attack is expensive and difficult on large, well-distributed blockchains. There is another kind of threat: key custody. If you lose your private key, your coins are lost forever. Centralized exchanges can be even riskier. Mt. Gox and Quadriga CX both lost access to massive amounts of user funds, not because the blockchain failed, but because the people trusted to hold the keys did. Blockchain's security model rewards honesty and punishes deceit, but only as long as the gatekeepers, miners, validators, or custodians do their job and no one holds too much power. A truckload of lettuce leaves a farm, its journey tracked at every stop. In 2018, Walmart and IBM tested blockchain to trace produce from field to shelf. A single QR code scan narrowed a recall from 7 days to just 2.2 seconds, pinpointing the source instantly. In digital identity, users now hold their own credentials, like diplomas or health records, secured by blockchain and controlled from their phones. No central authority is required, and no one else can alter or erase them. Cybersecurity teams anchor server logs to blockchain, making tampering impossible to hide. Estonia's health system uses this method, alerting officials the moment a log entry is changed. These examples reveal blockchain's reach, automation, provenance, identity, and security, working behind the scenes, quietly reshaping trust. Beneath blockchain's promise, hard lessons have shaped the code. In 2016, a bug in the DAO smart contract allowed an attacker to siphon off $60 million in digital currency. Those funds were locked and lost because the code could not be reversed. A parity wallet bug froze $150 million, trapping assets forever. These failures taught developers that once code is deployed, mistakes can be permanent. Even the fastest blockchains rarely process more than 20 transactions per second, a world apart from the thousands handled by traditional payment networks. To push past these limits, engineers built Layer 2 solutions like rollups that bundle hundreds of transactions off-chain and then settle them together, slashing fees and boosting speed. But with every shortcut or privacy upgrade, new trade-offs appear, such as more complexity, less transparency, or reliance on different trust models. Blockchain's guardrails are built not on hype, but on the scars of real-world failures and the checklist of hard-won solutions. Right now, over $1 trillion in assets move across blockchains with no central gatekeeper. As industries race to harness this trustless technology, the rules of ownership, privacy, and power keep evolving. The next shift in how we connect could be written block by block. What would you build?